Good afternoon. As was mentioned this morning in Mark's presentation, ECHORD was a precursor of the new mechanism of having the possibility of funding small-size experiments in a kind of open call framework. So the idea of the session this afternoon is to tell you about what's happening as a sort of follow-up activities to the ECHORD project. And I'm speaking about the agenda of this session. So I will moderate the session and I will give a brief introduction about EUROC, the new project which I coordinate. And then you will hear three presentations from three colleagues belonging to the core consortium of EUROC. Martin Hegele from Fraunhofer IPA, Rainer Bischoff from KUKA Labs, you heard him already yesterday afternoon and this morning, Christoph Ursuler from Alstom Power in Switzerland, and then Rainer Lafrenz, who was engaged with me as core consortium members in ECHORD, and now is engaged into ECHORD++, which is the follow-up activity to the ECHORD project, and is obviously from TU Munich. So this is just the contents of my presentation. And in order to illustrate the new concept that we've been promoting with this project, I have a video in the next slide.
The European manufacturing industry needs competitive solutions to maintain global leadership in products and services. To this end, some of Europe's leading robotics companies and research institutions have formed a consortium aimed at launching the European Robotics Challenges, EUROC. EUROC consists of three industry-relevant challenges within the themes of reconfigurable interactive manufacturing cell, shop floor logistics and manipulation, and plant inspection and servicing. Each of the three challenges consists of three stages of increasing complexity. Stage 1 is the qualifying stage. This includes a simulation test and a matchmaking event, where challengers can team up with end users, technology developers, and system integrators. The 5 highest scoring teams in each challenge will move on to Stage 2. Stage 2 is performed in realistic labs and consists of benchmarking, freestyle, and showcase rounds, before 2 teams per challenge are selected as EUROC finalists. The third and final stage will consist of pilot experiments at end-user sites under real manufacturing conditions. The results will be evaluated by a board of expert judges, which will eventually select one EUROC winner. EUROC presents some excellent benefits to participants, including a pot of €7 million in grant money, the opportunity to test and benchmark their algorithms using the latest hardware at real end-user sites, and incredible networking and business opportunities. The call for challengers will open from April 1st to June 30th, 2014. If instead you are an end user, technology developer, or system integrator looking to team up with talented challengers, this call will open from April 1st to mid-November 2014. So if you're interested in being part of this unique opportunity, or want to read more about who we are and what we're looking for, don't hesitate to check out our website at www.euroc-project.eu or follow us on Twitter.
So this was in 2 minutes 20 seconds EUROC in a nutshell. So you got an idea of what we are committed to pursuing in the next 3 years and a half. The project was kicked off January the 1st, but actually the calls were open April the 1st, as you saw in the video. And the 3 challenges, and you will hear more details about the 3 challenges in the next 3 presentations, are actually articulated into 3 stages. The first stage is the qualifying stage, which is only reserved to the challengers, whereas the end users, the system developers, and the system integrators, technology developers will go directly to the matchmaking. So this has a duration of 4 months, and the best teams which are teaming up with the end users. They will put up proposals, and they will work for a period of 10 months plus 5 months into the second stage, where the use case is emulated under realistic manufacturing condition in the lab. Then in the final stage, 2 challenger teams per challenge will advance to the field test, where the use case is brought to the field test, to the end user site. And this has a duration of 9 months. So the total duration of the project is 48 months, and you can see a number of milestones along the timeline of the project. In view of the focus of this I4MS event, I decided to have just one slide illustrating the concept of the matchmaking, which is of greatest interest to the companies and to the SMEs. So basically, a number of challengers register for the simulation contest, and those will be automatically scored, and there will be 15 winners, so 15 best-ranked challengers for each challenge. In parallel, there is the call open until November 15 for the end-user technology developers and system integrators, and we do hope to scout as many SMEs as we can. Those SMEs that maybe they haven't solved yet their use cases using robotics technology, but they have a sort of potential to solving their use cases using a technology as far as it fits in the 3 scenarios of the challenges. So basically, those companies, they submit either use cases or technology or expertise, and they have to provide a description of what they want to contribute. So there is an elicitation, and then we will have a folder, a catalog of use cases. This is a similar concept to what we had in the ECHO project, where the companies were offering hardware, firmware, software, and there is a folder of technologies, and there is a folder of system integrators. And then there is a matchmaking phase, which will culminate into a brokerage workshop. We will be coaching this activity, in which the 15 teams which have qualified after the simulation stage will pick up one use case to solve. And this is very competitive, because if you are a challenge team, you can bring your end user to the party. But at the same time, you have to accept that this is competitive. So this end user may find a better team, or you yourself as a challenge team can find a better use case to compete. So you pick up your use case to solve, and then you pick up some technologies which are needed to implement the use case, and only for the first challenge, you will hear more details in a while, you will need a system integrator, because the first challenge is completely open as far as the technology developer and the system integrators are concerned. And then you team up and you come up with a small consortium. This is a la ECHOD and ECHOD++ and other experiments which now are part of I4MS, and then you prepare a proposal. And the proposals will be judged according to the same criteria as the project proposal evaluated by the European Commission. With independent experts, we have to be neutral in the core consortium to the evaluation, and there will be a consensus panel. But basically, we'll have 1 chance out of 3 to be funded, because of the 15 teams, 5 will be actually funded. So this is a challenge chart summarizing the whole process in the 3 stages. So we expect as many challenge applicants as we can in the simulation contest. And then in order to participate to the matchmaking course, in which you may have to meet some end users and also you have to attend the final brokerage workshop, we will grant a sort of reimbursement, argent de poche, we can say, of €5,000 for the teams which have borne some expenses to be part of the matchmaking. Then, the most interesting part in terms of the financial support comes in the second stage, where each challenge team can be supported for 250 plus 125,000 euro, and then the pilot experiments in the final stage are supported 210,000 euro. So in the final slide, I try to summarize why you should find advantages. What are the allures of applying to Europe project? There's a cumulative sum of 7 million grant money available to the challengers into the 3 stages. So in the 6 lucky teams that will be in the final stage will have received a total support of 585,000 euro for 24 months of work. And this should be quite appealing. You saw in the video that there will be symbolically 1 Europe winner, because we can't use European taxpayers' money to grant an award and a prize award, like for instance DARPA challenges do in the US, because we are in Europe. We do this with different culture and with different rules, okay? The second lure is the added value of the challenge experiments, because you will have the possibility of benchmarking. This was underlined several times during the presentations of yesterday as well as of this morning, but there is a time, and there is now a time of benchmarking the algorithms to facilitate the technology transfer from the research lab to the industry. And this is perfectly in line with the work program of Horizon 2020, by the way. And you will be able to benchmark these algorithms on 3 first-class European hosting platforms. For the involvement of the so-called whole value chain, because from the beginning, from the time of the proposal, the end user, the technology developers, and the system integrators are on board. It's open access to platforms, so this is an advantage, with full support from the local host and also from the end users in the final stage, at the end user site, and also where you will have the possibility of testing the algorithms. And as far as the financial support, there is no durable involved, because either you bring your hardware or you find your hardware and the system integrator expenses by the platform host. So basically, this money is good for personnel, travel, and subsistence. And also, during this matchmaking phase, there is an excellent opportunity to gain business experience, because you will team up with the end user from the beginning, and also great networking opportunities. And this doesn't rule out the possibility that in the final stage, if you're not qualified to the final stage, you will have received the support of 375,000 euros. So you may find advantageous to continue your experiment at the end user site, even without our financial support. So those are the dates. Both calls were published April 1st. In 12 days, the call for challengers will be closed. You don't have much to do other than registering an application, like a one-page profile, who you are, why you want to apply to that challenge, whereas the call for end-user technology developers and system integrators will stay open until November 15, in such ways to allow us to give more time for the scouting of those companies and SMEs which are potentially interested in the project. You can follow us, you can email us. There's a website, the video is so, there's a press release, and there's also a nice seeker spotlight at Innocentive, which is a company in our consortium, and they are the world experts of challenges. They have carried out more than 1,600 challenges, and they've been the company in the US that has run all the DARPA challenges. So that's why we wanted them to have them on board, and they're also partner in the Rockin initiative, which Rainer mentioned this morning in this presentation. You can follow us on Facebook and Twitter.
I have the pleasure to introduce the first scenario, the first challenge, which is titled Reconfigurable Interactive Manufacturing Work Cell. Or actually, work cell should it read, it's a robot work cell. And in fact, what actually motivates us to bring this scenario forward, of course, we have the vision of using a robot as intuitively, as safely as we use today a power tool. And two characteristics are quite evident from the title, that we actually think about work cells which are used interactively, which means in a safe way, in a cooperative way, in also an informational, intuitive way, and that the work cell is reconfigurable. We also put the process of assembly into the focus. And if we look at today's robot application, industrial robot applications, we see that quite few, or relatively few, are actually used in assembly. And this has a meaning. This is because the assembly process, in terms of robotics, is quite complex. We need motions, but also motions which are influenced by tactile information, by compliance, etc. And this process, which is an encapsulation of tactile information, motion information, sensor information, is quite difficult to program or instruct. So that's why we are also looking into that process. So we will define scenarios, and as I already said, we'll put the adaptive perception, cognition skills into the focus. We will look for robust assembly, and of course also emphasize safe and productive human-robot interaction. especially when it comes to cooperative assembly, the aspect of workflow, of economic feasibility, profitability comes into play. So is the process really conducted in an effective way? So there's a perfect way to actually evaluate this in realistic scenarios. Another thing is that we also think about using more than one robot, multiple robots, that we have also robots act as a fixture, as a positioning tool, etc., and have the other process robot work as a process tool. So these are examples of the scenarios we'll be looking at. We'll take these scenarios out of industrial application scenarios. In fact, we will be running in Stuttgart, or we already started with that project more than a year ago, with a so-called ARENA 2036 scenario, which is actually a research factory. ARENA stands for Active Research Environment for the Next Generation of Automobiles. So it's a large initiative promoted by Daimler, Bosch, and many other automotive manufacturers, automotive supply manufacturers in the Stuttgart area. And one of the activities is that we are setting up a complete research factory. And in fact, we'll be taking use cases from that research factory on the one side, and also ask the teams to implement their solutions on workstations in that research factory. So we will have an extremely realistic demonstration and evaluation environment, which should of course also be attractive to other teams to get in contact with advanced automotive manufacturing. Also, part of the ARENA is that we provide state-of-the-art hardware of quite many manufacturers, both on the component side, also on the system side. Examples are listed here. So these teams will find a very rich set of hardware. Also, we will provide as EPA the glue to actually integrate components. ROS has been mentioned a couple of times yesterday, so we'll be offering that kind of interface for teams to integrate components. And of course also EPA will help and assist these teams to bring their integration or their solutions forward. Yeah, as Fraunhofer IPA will be soliciting for applications, of course. Also we will assist in the hardware setup, software integration, and all other works which come with robotics engineering and robotics use today. Yes, and contact persons are myself, is my colleague Rames Abad and my colleague Bernd Winkler, and I'm of course very much inviting you to consider participating in this challenging effort. I certainly can promise it will reach highest visibility.
Good morning, everybody. So my talk is a little bit different than the ones that you have seen before, because I'm concentrating on how KUKA is innovating in this whole process of innovation in Europe. My name is Rainer Bischoff. I'm the head of technology development of KUKA Laboratories, and I'm also the vice president of the Robotics Association, eRobotics ASBL, and you will see how this is all connected in my presentation. So KUKA is known as the world's largest manufacturer of industrial robots for the automotive industry, and you see here our three companies, KUKA Roboter, KUKA Laboratories, and KUKA Systems. And in the low row you can see also how our business is distributed to the different sectors. And just from the figures that you see below, automotive 50% on the KUKA Robotics business, and even 90% on the KUKA Systems business, you see that we have a high dependency on the automotive industry. And what we try is to diversify and also to bring our robot technology in different branches of the industry. And therefore we founded KUKA Laboratories. KUKA Laboratories is a company that is now developing robotics technology also for the medical sector. But if you want to put it in short words, it's our service robotics company. And I have been asked to point out in my presentation about the innovation that we are doing with industrial robotics. Industrial robotics, of course, there has to be, we have very close relationship to our customers. So customers are at the heart of our business, and this is already driving one part of the innovation. But if we only listen to our customers, you know probably the famous sentence from Henry Ford, if I had asked my customers what they wanted, they would have said a faster horse. And the same applies to robotics. So no one would have ever said, would have come up with the innovations that we have come up in the past years without a technology push where we really rely on a close collaboration with academia. And this is how we see the innovation potential in the robotics business today. So we all know the industrial robotics business. We have PC-based robots controllers. We know offline programming, and we like to refer to this as the first robotic revolution that happened with the advent of these industrial robots. Now we are at the borderline to the second robotic revolution, and this will happen because we have very good knowledge about the mechatronics of our systems, about how we integrate safety with these robots and how we do more simpler programming and operation of these robots. And here you see depicted the KUKA lightweight robot, which is compliant, safe, and this will allow us from now onwards to go on with the second robotic revolution. And on top of that, we try to make these robots mobile and to yield mobile manipulators, which would go to the third robotic revolution, where we combine mobility and manipulation, where we have more intelligence on board these robot systems, and where we go from a programming to more intuitive operation. So I'd like to focus now on these three steps of the robotic revolution. So first looking again at industrial robotics with the PC-based controllers. If you just look back, this was one of the key innovations that we did already in 1996 to switch from proprietary controllers to an open PC-based controllers. If you just see at the number of robots that had been produced until 1996, this were 12,000 in total over the years. And since we introduced the PC-based controller, we had a major rise in our business because the PC-based controller was open and many customers were following, and now all major robot manufacturers are using PC-based robot controllers. Second example, in 2010 we introduced a new robot series, the Quantex series. This is one of the things that we try to bring in the potential from mechatronic technology development. We always have to reduce the volume of our robots, to reduce the weight, so that we can reduce also energy consumption and to be faster in our production. This is one thing. And then another thing is how we are going to save on spare parts and how we make the life easier for our system integrators to maintain and repair, for instance, robots. We simply replace hardware by software. So ICT technology is very important for us here. Energy efficiency for a sustainable production is important. For instance, by forecasting the consumption of robots in simulation is one important aspect. But also important are the manufacturing processes. So we are still developing new joining processes. So if you think that welding is a solved problem, it is not. So even in welding, you are able to innovate. And for instance, what you see depicted here is a robo-spin technology. When you just look at simple spot welding robots that are used nowadays, they simply go from one spot to the next, to the next, to the next. But there's still an innovation potential. If you just rotate the welding gun while you are pressing the material, you can already save some time while you are moving, and you can also save your welding gun, and the welding gun tips are much better used. So there's always new things to detect and to develop. One part is also energy efficiency. This is a nice, interesting figure. So from left to right, you see some of the robots in a typical automotive production. So only 19% of the time our robots are actually in motion. 81% of the time they are not in motion. So we have to look into this, why they are not in motion. So some 10% of the time they are stopped with active drives, which means there's no brakes engaged. Then they are stopped 26% of the time with brakes engaged, stopped 10 minutes, from 10 minutes to 3 hours, and they are stopped over the weekend for 28% of the time. But what is happening, our customers are not switching off their plant. They keep it running all the time, so this means there's a huge potential here to save on energy. And we did something in that area, on each of these areas, only a little bit, but as I explained just now, the Quantex series, because it's more lightweight, it's already saving energy while it is in motion. Then we have a technology called blended braking, which engages the brakes much earlier than before, which saves energy. even if you think this is a little bit ridiculous to have a temperature-controlled fan, it is also helping us to save energy here. And then there are simple standby modes that you all know from a PC technology. You can send your PC into sleep mode and save more energy. And now this is also possible with robot controllers. This might sound simple, but the difficult thing is to wake up the robot controller after it has gone into sleep mode, and that all the peripheral equipment is coming up again as well. So through these technologies, we are able to save energy on the shop floor. So very important aspect in industrial robotics. But as I mentioned before, the major innovation step came from the PC-based controller, and all the other innovations are then adding incrementally on that level. So the next disruptive change in robotics is through the compliant and safe robotics technology. The KUKA lightweight robot here, you can ask why we have developed that robot, and this is because we need sensitive robotics on the shop floor. To enable totally new assembly concepts, to enable the collaboration between humans and robots, and then most importantly, to relieve the worker at unergonomic and bad workplaces. And finally, to keep production in high-wage countries. So that's why we need this robot system. And what did we do? We integrated torque sensors, and we integrated safety technology on drive level. And this integrated safety technology is complying to the norms. This means ISO 10218, performance level D, and structural safety category 3. There's a lightweight construction in this robot, and we have a powerful operating system to make it easy for the customers to program and to operate it. So the robot is called IVA, an intelligent industrial work assistant. And I give you a few examples on what can be done with the robot system. First of all, I highlighted now in orange, that's the kind of functionality that is now enabled by the robot. And to give you an idea about the functionality, I have 4 videos. That should pop up now on the next slide. Without the sound, please. Okay, so here you see the interesting features of that robot system. So first of all, to the left top corner, you see the gravity compensation that is enabled by the robot. So while the robot is carrying 7 kilograms, you can easily move the weight around. So you can, for instance, teach the robot by demonstrating where to move with the payload. It's just 100 grams that you need to move the robot, but still it has a payload of up to 7 kilograms. Then to the right top corner, you see the kinematic redundancy. It has 7 degrees of freedom instead of 6. With these 7 degrees of freedom, you can reach around corners, you can reach difficult situations on your workplace. And in the lower row, you see a special feature that looks like a spring. It's basically like a human arm that you can push away that has also certain damping characteristics and certain stiffness characteristics that you can program on an axis or joint level, but that you can also program on a Cartesian level. And what you can do with these nice technical features, we have to demonstrate with our customers so that they see what they can use. Here is a picture of a manual assembly of a differential gear. So that's a very difficult and unergonomic situation because the gear is heavy and you have to use your both arms to fiddle this gear into the gear house. Daimler did this with a very complex gripper technology. So to the left you see depicted this gripper. It is very complex. It has, in order to do that compliant motion, it needs mechanical compliance. This gripper has low flexibility. It's only working for this type of gear. It has complex engineering. Just look at the picture, and is associated to this high cost. Now the simple solution with the lightweight robot is you can have much simpler grippers because all the compliance that you need is inbuilt into the robot arm. So you compensate through software. This gives you high flexibility, gives you much more simpler engineering, and then accordingly low cost for the grippers. I have a video here on how this is being used at Daimler today. This is a rear axle transmission assembly, which was done manually and then with a complex gripper. And now we have the lightweight robot, which is able to lift with the help of a balancing system this gearbox, or the gear, which is then inserted into the gearbox in a kind of dual arm setup operation. So the second arm is coming from below, and both together they are pushing this into the housing. And then you see an operation that also a human would do. There's a kind of shaky motion at the flange that you see. So the robot is moving like this, and this is helping to fiddle in the gear into the housing. So the same operation that a human would do can now be done with these robot systems with much simpler grippers than it was able before. So now to focus on the second, so this was the sensitivity aspect, which is very important for robotics of the future, or for the automation of the future. The second important aspect is now highlighted in orange, and that's the collaboration between a human and a robot. And therefore you need to have safe robot systems which comply to the safety norms. And why this is important? Because the system integrator in the end has to do a risk analysis for the cell that he has to set up. And he has to make the certification of that cell so that the end user is able to use the system. And what is important in this respect is that we are now able with this robot to not only program a velocity for the robot, but to guarantee that this velocity is not surpassed, even if an error in the hardware is occurring or if an error in the software would occur. So safe velocity monitoring, safe workspace, and safeguarded zones. This is also needed to set up human-robot workplaces. Safe collision detection, safe force monitoring, safe tool detection is also needed. You need to know what kind of tools are put to the robot, and safe switching of states. And all this in performance level D, category 3. This is something for the experts. If you don't have this performance level, you would have a hard time as a system integrator to justify why you can remove all fences around the robot system. Also a video to demonstrate what we actually mean with this. So here you see someone again guiding the lightweight robot, and you also see the workspaces that have been set up. So the robot would not be able to go outside these virtually set up workspaces, the fences. There's a velocity monitoring integrated in safe technology. This means if the robot is moving too fast, it will simply stop. And then this safe collision detection. First, the crushing. So crushing means that the robot wants to insert something, but then detects that there's a human hand inside, and the robot is able to detect that and will automatically retract. Or the safe collision detection in a free collision. So when the robot and with the tool are going to the human, the robot will notice this and then can continue with the process. Okay, this brings me to the third revolution. We have to put these arms onto mobile platforms to be able to simplify the shop floor logistics and manipulation. There's one example now. Now we are going to the future. So this has not yet been realized or just in research projects. We are engaged in many research projects in robotics. One of them is TAPAS. And here we are collaborating with Grundfos as an end user. What you see here depicted are some examples of a Grundfos shop floor. To the left, you see a machine tool. This machine tool has to be fed by the robot system. To the top, you see a quality station, also to be served by a mobile robot system. If you want to move around on the shop floor, you need things like lifelong mapping and local navigation. And there's also manual workstations that just have to be served by such a robot system for simple assembly tasks. And here I have just a video that we did recently at Grundfos for our final evaluation. You see that we are far from having done this at a level that this can be used at a production, but it just gives you an idea that you have a robot that is now able to fully autonomously navigate on the shop floor, so no additional markers are needed. And then you can use the robot to feed workstations. You can use the robot to pick up objects from location A to bring it to location B. Here you just saw the robot switching off a conveyor belt by using just its own motion capability to stop the conveyor belt and then be able to pick up the object. This robot is equipped with an external stereo vision system. It has autonomous path planning for the robot arm. And what you also see, the video is much accelerated. Actually, it's accelerated by the factor 8. So this also gives you an idea that this technology is not yet ready for the shop floor because we are too slow with all the nice scientific things that we are doing So there's still an order of magnitude, or maybe even 2 orders of magnitude improvement needed in this case. Navigation is quite reliably already. So these are some of the challenges that we still see from a scientific and also from an industrial point of view, which would make nice projects. Each of the lines that you can see here should be targeted by researchers. And what makes it even more important or even more difficult, if we look into the industrial requirements that go all along with these scientific challenges. So you have to reduce the setup time of such a system. In the Grundfos scenario I just demonstrated, we had 2.5 days to set up the whole system. This is much too long, so this has to be set up in 2.5 hours, not in 2.5 days. Cycle time, I mentioned already, video was much accelerated. The dependability, it has to work 100%. Technology readiness is not there yet. And of course, the cost is much too high to really be of help to manufacturing companies. So if you look at these core technologies for mobile manipulation, you all know these terms: end effector, safety control, locomotion, navigation, sensor, sensing and perception, human-machine interface, planning, learning, system architecture, system engineering tools. All these are core technologies that we need for mobile manipulation. A very important question is on how to combine all these into one system and what technologies to use. So there's one thing, so how to integrate them into a complete system, how to achieve reliability, and I'm standing here saying, so this is long before it will be applied into the industry, so further research and development is definitely necessary, and the big question is, what is KUKA doing to speed up this process? And I have 2 answers to that. So one answer is we are trying to drive innovations through collaboration with academia. We are very much engaged into the EU Robotics ARSBL, that's our European Robotics Association. We do now have more than 180 members from industry and research. About 1/3 is coming from industry, 2/3 are coming from research. And this EU Robotics ARSBL is also the private side of the public-private partnership with the European side. It was introduced yesterday already. It's called SPARK, the Partnership for Robotics in Europe. And through this partnership and through our colleagues from industry and research, we try to set up a roadmap, and through that roadmap then, of course, to influence the research that is being done in the field of mobile manipulation. So next slide is not coming. Maybe you can do that manually. So there's a collaborative road mapping process in EU Robotics ARSBL. Of course, it's important to be a member, to be able to vote on priorities, but also non-members. If you think you are an expert and can contribute to these technologies, you are invited to collaborate with us in the so-called topic groups. And these topic groups are then giving their input to our strategic research agenda. That's a high-level political document. And then, most importantly, to the multi-annual roadmap, which will be updated biannually and which is then used to discuss with the Commission what could be priorities for the next calls. And this collaboration is, I think, really driving us to innovation in the long run in robotics as a whole. And the second answer to the question, what is KUKA to speed up the process, we are developing robots that can be used in research and that can be used or that can be seen as standard tools for education, application development and research. Here's the KUKA U-Bot as one example. It's a mobile platform with an industrial but little robot arm. It has real-time EtherCAT communication. It's the same communication we use in our big robots. It's freely programmable. There's open source library available. And we think that it's important to have such standard platforms to enable researchers to focus on their research, to benchmark their research with others, to participate in competitions, and to better market their results. Because if this becomes comparable through the use of standard platforms, it's much easier for companies to compare. So this brings me already to the last slide of my presentation, summary and conclusion. I think that research is very important. Although I'm standing here as an industry person, I think we should not neglect the research part. And many of the technologies identified in the European Strategic Research Agenda are needed to realize mobile manipulation for the factory of the future. Then the second thing is that integration is important, but we have to avoid to reinvent the wheel by always developing new robot systems. You should also try to use standard platforms which help to reinvent the wheel. I think also that competitions are important, and there will be a session in the afternoon on competitions related to EUROC, the European Robotics Challenges, but there's more competitions around. Also KUKA has just recently spent 20,000 euro for the winner of the KUKA Innovation Award, which was on the area of mobile manipulation. And these competitions are important to create a better awareness and to allow for benchmarking. And last but not least, collaboration is important. To collaborate not only within the industry players, but also between academia and industry. And here we have two major initiatives, our Robotics Association, please apply for membership, and Spark, the program for robotics in Europe. Thank you for your attention.
Okay, good afternoon everyone. My name is Christoph Hörzler. I'm with Alstom Power, but today I'm actually speaking for Alstom Inspection Robotics, which is a smaller independent spin-off of Alstom, which is really focusing on developing new inspection robots. What I will talk to you about today is basically focusing on aerial inspection of different power plant facilities, or in general industrial facilities. And regarding the motivation, maybe you allow me to quickly give a little bit Alstom perspective on the problem. So if we think about power plant servicing and maintenance, then often it is underestimated how valuable it is to just look at specific subsystems or components of a power plant, because this can already, just looking at a specific component and its state can give you a tremendous amount of what is going on, of information about what is going on with your power plant. Now, problems there is either the components that you're interested in are in a very confined space, so they're very hard to reach. So you need, for example, a crawling inspection robot to bring a camera into a specific structure and look at a particular component, or what you're interested in is an industrial structure that is very vast, very large scale. So, for example, it could be a typical application like a large steel chamber, basically, and at 80 meters height, there's a specific component, and you want to look at that component. Now, what you can do is shut down your power plant or part of the power plant and build scaffolds to go up there and look at the component. You can try to have an industrial climber try to get to this particular component. All of that is a lot of work, of risks, of course. So if you just had a small eye in the sky, basically, a flying camera that you can send up there quickly, and it looks at the component, takes camera images, that would be of tremendous value. Now, there are some challenges involved there. The most particular one is that basically in the infrastructures we're talking about, you have no position measurement for the aerial vehicle. So outdoors, you generally have a GPS signal, so you can localize the vehicle, and then through that, basically you can implement certain control algorithms, which then allow you to in a very simple way operate or fly the aerial vehicle. Indoors or in the facility components which we're focusing on, this is not available, which makes this vehicle very hard to pilot in this infrastructure. Imagine again at 80 meters height, you just see a small black spot in the best case representing the UAV, and now you need to operate that UAV very close to a specific structure. So you need some sort of support for the operator or the pilot there. And for that, you need a sensor system, basically, that gives you information about where is the UAV, in particular with respect to its immediate environment. Now, one big challenge there is that basically we're now operating really in complete 3D space. That means if we talk about collision avoidance or collision detections for our UAV, an obstacle in our case can come into contact with the UAV from any point or any direction. So they're basically, in the best case, there would be sort of like a virtual sphere encompassing the UAV platform, which senses if an obstacle is coming near and then prohibits the operator to move the UAV further in this direction. There's also the problem of robustness. Like if we just put one sensor on there that gives us a position, for example, what happens if this sensor fails? Then we're back to the problem of we have nothing that supports the operator operating the UAV, and we will probably crash the UAV immediately, which is also a problem because then basically we interrupted the plant operation for servicing, and now our servicing tool broke, and we need to repair it or get a new tool, which is time we lose, which we might not want to lose. Now, coming to more to the challenge itself, basically what is provided to the challengers as a platform, as tools, which they work with. The core idea here is really they shouldn't focus on just making something fly, because we consider that a solved problem. So what they will basically get is a flying platform, a small flying platform from a German company, Ascending Technologies. Roughly this form factor, this size, which means it's rather safe for the challengers to use, and later on in an industrial application, again, it's safe for a human operator to work with this vehicle. Additional, there will be at least one sensor, a stereo camera, which is sort of targeted at the UAV application per se. But then in the background, the idea is really that the challengers add other types of sensors for the robustness, and then really work on the algorithmic part, using the sensor data to localize the vehicle with respect to the environment. There, of course, will also be an SDK to interact with all, or SDKs, to interact with all of this hardware and the software simulator. In terms of support, the challenge hosts will be two laboratories, two departments at ETH Zurich in Switzerland, one of which is the Autonomous Systems Lab, and the other one, the Institute of Dynamic Systems and Control. And both of these departments, both of these laboratories already have a tremendous amount, years of experience dealing with these types of platforms, of vehicles, and the problem itself of controlling these vehicles also in challenging environments. So there will be plenty of experience and support there. Then we have, of course, the technology developer, Ascending Technologies, which provide the platforms and also support dealing with the platforms. And there's the system integrator, Alstom Inspection Robotics, which will basically support the challengers to focus on the correct problems, like what are the parameters or challenges in terms of environment that they should focus on. As contact points, we have Markus Achtelik from the Autonomous Systems Lab, ETH Zurich. We have Daniel Gurdan from Ascending Technologies, and Eckhard Zwicker, who unfortunately couldn't be here today, from Alstom Inspection Robotics.
My name is Reinhard Laffrenz. I'm from Technical University of Munich in Germany, and I'm not connected to the EU Rock project, which was presented so far, but I'm from the Eckhard++ project, which is a different scheme. We are not part of I4MS, but as we run different schemes, it's worth being integrated, and I thank the organizers to get this invitation to present this project here. So, first of all, the motivation of the Eckhard++ project has a long tradition. We already had a previous project, the Eckhard project, which was mentioned already in many of these sessions, starting from the very beginning, from Khalil Rouhana's presentation in the morning. This project ran over the last 5 years, from 2009 to 2013, and the main instrument distributing money to the community were the so-called experiments, which were already mentioned in several presentations in addition. So now we have the Accord++ project, which adds 2 additional instruments to interact with the community. I will come to this point later. But what is the main idea behind? The main idea, what we want to create, is impact. We want to have a clear outcome which is close to development of applications, which has a real benefit for the community, for Europe, and SMEs, small, medium-sized enterprises, are one of the main target groups to be addressed here in this overall project. From the application side, we have grouped our work into different scenarios so that an applicant has some guidelines on where to apply. It's not as concrete as in the mentioned areas here, so we don't have a certain number of applications for the different scenarios. We just offer this structure as a guideline on how to write your proposals for the individual experiments. The scenarios range from cognitive tools and workers for cognitive factories, which is mainly related to manufacturing, which is the focus also of the I4MS initiative. But we have also general purpose core workers, which goes into the direction of human-robot interaction, starting from easy programming up to real physical interaction. So we are very open on what type of applications we like to see. But we also have one scenario on cognitive logistics, especially for robotics in industry. But we also tried to include new scenarios which look promising and where at least we identify a high potential of automation and including robotic technologies in these areas. And those are medical robotics and agricultural and food robotics. The overall concept of the Accord++ project is relatively simple. We started with a small group of core partners who already fulfilled the requirements for European projects, namely 3 partners in 3 different countries, so that every sub-project, every experiment which joins us later on is highly flexible in choosing their own partners. So it could even be 2 partners from 1 different country who form a small consortium to go into one experiment. So besides ourselves, Technical University of Munich, we have additional partners at BRL, British Robotics Laboratory, from UPC in Barcelona, CEA in Paris, SSSA in Pisa, and we are just about to add 2 additional partners, Blue Ocean Robotics in Denmark and RU Robots in Great Britain. So Accord++, in a nutshell, I mentioned already that we have 3 main instruments to interact with the community. The first one are the experiments. These are small-scale sub-projects, so we are talking here about small consortia of 2-3 partners and a typical funding volume of 300,000 euro with a runtime of 18 months. We will issue 2 open calls. One is already passed, so the deadline was April 14th, but you still have the chance to apply for the second round. All the scenarios are open in both calls. For the first call, I will give you some statistics about the proposals we received, and the main idea behind is to get these relatively close to the application, developing almost prototypes in the mentioned scenarios, and to see what the outcome is. But we also try to follow up on these experiments later on throughout the lifetime of the project and hopefully even beyond that. The second pillar we have here are so-called robotics innovation facilities, or in short, RIFs. This is another way of interacting with the community like these already mentioned competence centers. What we want to have is physical infrastructures where people can, without any bureaucracy and without any direct interaction with EU funding mechanisms, come, try something out, get access to hardware, to software, but also get access to experts who might support a specific development. And this is an instrument specifically designed for SMEs, but also open to all other user groups. And we will have 3 physical infrastructures, one at our partner in Bristol in UK, one in Peccioli close to Pisa at SSSA in Italy, and the other one at CEA in Paris. So one of the most impressive benefits here is that you don't need to run through the amendment request. You can just apply with a 2-page application form. You formulate your idea, and once you are accepted and scheduled, you can just come try out, but you can also attend workshops and interact in a different way. The third pillar we have here is pre-commercial procurement pilots. This will be 2 prototypical installation areas where we want to engage with small research and development consortia, namely companies, which is also very closely related to SMEs. And these installations will be done at public bodies which are currently searched for. So if someone here is from a public body in the area either of healthcare or of smart cities and interested in getting an installation and has a use case in mind, yeah, please contact us here. So this instrument is done for a demand-driven development by R&D consortia, and given the time, I cannot go into the detail here, but if you are interested in this instrument, please feel free to contact us. So for the Call 1 deadline, which was April 14th, we received 137 eligible proposals with 348 partners in total. And of course, the emphasis was on impact-oriented cooperation between industry and the research community, and that we well addressed this target can be seen in the statistics. For example, you can see that we have roughly half of the applicants being from research or non-profit organizations, and the other half from large industry, small industry, and some other things like public bodies. But if you have a closer look into the SME participation, it's roughly a third of the applicants are from small, medium enterprises, and thereof there is a significant share of new SMEs which never attended to or never applied for European funding. So we were able to recruit some new small companies to engage with us through this ECHOT mechanism, and maybe it's helpful that we act like an intermediate instance between the European Commission, who gives the money, but we ourselves, being researchers, understand what the complications or the main barriers are if you try to apply first time, especially as a small company, for European funding. If you are interested in participating in one of the next calls, please feel free to follow us here on the www.eckhart.eu or with our LinkedIn group, so you are still able to submit a proposal for the next call, which will be mid-next year. Short words on the robotic innovation facilities. As I mentioned, we have 3. I don't run through the list, but as you can see here, we have different areas addressed by the different physical installations, ranging from manufacturing over agriculture up to rehabilitation robots. And if you like to engage with them, just go to our webpage, see the individual specifications where already lists of hardware and services which are provided are given, and the RIFs will become fully operational roughly by the end of the year. Currently we are in beta testing phase, so I cannot tell you exactly how long it will take until things are fully set up, but expect by the end of the year. The idea here is that we have a stay duration of up to 6 weeks. You can have a re-application if your stay in the initial phase was successful. We don't have any fixed application deadlines, but we will have a selection panel roughly every 2 months, and maybe this is beneficial for those who are hesitating to go into formal European funding. You don't need to run through the bureaucracy, you don't need to become a formal partner, you can just go there, try something out, go back with the results, and we will come back to you and ask you after 6, 12 and 18 months what the results are and whether your stay was successful or not. The intended user groups here are mainly SMEs and startups, but also, for example, students could come, new user groups, maybe we find some psychologists doing studies on human-robot interaction and things like that. And in addition, we ask the experiments to go to the RIFs and to demonstrate the results at those RIFs. And of course there will be much more activities than just the actual stay. We will have workshops, we will have additional events to interact with the community and to attract new companies and other users. If you are interested in getting in contact with us, just write us an email, visit our website, or join us in the LinkedIn group. And now I'm happy to receive questions.
Sure, thanks.
Thank you very much.